Right now, deep inside every atom in your body there is a storm. Scientists can measure it, and it still amazes them. The proton, the tiny heart of matter, weighs almost 1,000 times more than the pieces trapped inside it. The math should break. Yet here you are, solid and real. So where does your weight really come from? Today we shrink down into the proton. We meet weightless particles that create almost all of your mass. We watch the strongest force in nature tie pure energy into a knot, and we find 3 tiny specks hiding a secret about who you are. If wonders like this pull you in, take a second to like and subscribe, then hold on tight. We're about to go smaller than anything you have ever imagined. Prepare yourselves. We begin. Hold up your hand and look at it. It feels solid. It looks like one smooth piece of you. But your hand is really a giant crowd. It is packed with tiny building blocks called atoms, and there are more atoms in your hand than there are stars in the entire night sky. Far more. Each atom is almost completely empty. Picture blowing one up to the size of a football stadium. The only part you could actually touch would be a single grain of sand resting on the center of the field. Everything else, all that huge space around it, is empty. That grain of sand in the middle is called the nucleus. It is the core of the atom, and it carries nearly all the weight. Now shrink your eyes down and stare at that grain. Inside the nucleus sit even smaller specks. Some of them are called neutrons, the rest are called protons, and the proton is the star of tonight's story. Here is the first strange thing. A proton is unbelievably tiny. Line up 10 trillion of them in a row, and they would barely stretch across the width of one human hair. You could never spot a single proton, even with the most powerful microscope ever built. Yet this little speck holds almost all the weight of everything around it. Think about what that means for you. Your bones, your blood, your brain, the phone in your hand, the chair beneath you. Weigh any of it, and nearly all of that weight comes from protons and their neighbours packed into the cores of atoms. The rest of each atom is mostly nothing at all. So the proton is more than some dusty science word. It is the reason you have weight in the first place. It is the reason a rock is heavy and a mountain is enormous. Pull the protons out of the world and everything you know would weigh close to nothing. For a long time, people thought the proton was the end of the road, the smallest piece. A solid little ball sitting at the heart of matter, with nothing smaller hidden inside it. Simple, clean, finished. They were wrong. When scientists finally found a way to look inside the proton, they got a shock. It held no solid ball at all. It was full of moving parts, tinier things trapped within it, swirling around at speeds that are almost impossible to imagine. The proton turned out to hide its own secret world, and that secret world holds one of the biggest riddles in all of physics. It is a riddle about weight, about where your weight truly comes from. The answer will flip everything you think you know about matter, about mass, and about your own body. Because when scientists finally cracked open the proton and weighed the pieces inside, the numbers refused to add up. And they did not miss by a little. They missed by a staggering amount. What they found should have been flat out impossible. Somewhere inside that speck, almost all of your weight is being created out of something you would never expect. Something that has no weight of its own. To understand how that can happen, we first need to meet the tiny things living inside the proton. There are 3 of them. Physicists gave them a strange, almost silly name. And once you learn that name, this mystery only sinks deeper. Back in the 1960s, a physicist named Murray Gell-Mann was staring at a puzzle. Protons and other particles were behaving as if they had smaller pieces inside them. Pieces nobody had ever seen. He needed a name for these hidden bits, and he picked a weird one. Quarks. He borrowed it from a strange line in an old book, a serious idea wearing a goofy costume. At first, the quarks were just math on paper, a clever trick to make the numbers behave. Many scientists doubted they were real. Then, at a giant machine in California, researchers fired beams straight into protons and watched the beams bounce back at odd angles. The beams were hitting something hard and small buried inside. The quarks were real after all. So here is the picture the world settled on. A proton is built from 3 quarks. 2 of them are called up quarks. One of them is called a down quark. 2 ups and a down locked together in a tiny bundle. That combination is what makes a proton a proton. Change the recipe a little, and you get its neighbour. 2 downs and 1 up build a neutron instead. Swap the pieces, swap the particle. These 2 recipes, sitting side by side, make up the cores of every atom in your body and in every object you have ever touched. For years, this was the clean and tidy story. A proton was 3 little balls stuck together. Teachers drew it on chalkboards. Textbooks showed 3 happy circles inside a bigger circle. Simple enough for a kid to sketch. And that picture feels right, does it not? If you smash 3 marbles together into a bag, the bag weighs as much as the 3 marbles combined. 3 heavy things make 1 heavier thing. That is how weight works everywhere in your daily life. Put 3 apples on a scale and you get the weight of 3 apples. Nothing surprising, so the plan seemed obvious. Find out how heavy each quark is, add the 3 of them up. That total should give you the weight of the whole proton. Case closed. The quarks themselves are almost unthinkably small. Even the proton is a giant next to them. If a proton were blown up to the size of a whole city, a single quark would still be smaller than a marble rolling around inside it. These are the tiniest bits of matter we have ever found. As far as anyone can tell, they have no pieces inside them at all. They may be the true bottom floor of everything. Scientists spent years working out how much these little specks weigh. It took huge machines and careful measurements. Slowly the numbers came in. They finally had a weight for the up quark and a weight for the down quark. Now the moment of truth had arrived. Take 2 up quarks, add 1 down quark, punch it into a calculator. Out should pop the weight of the proton, the number that has been measured 1,000,000 times over in labs around the world. The scientists did the math. 2 ups, 1 down, all added together. And the answer that came out was so far off, so wildly, laughably wrong, that at first it looked like somebody had made a terrible mistake. The 3 quarks inside the proton barely weighed anything at all, which meant the weight of the proton had to be coming from somewhere else entirely. To feel why the answer was so shocking, you first have to understand how physicists weigh something 1,000,000,000,000 times smaller than a speck of dust. You cannot exactly put a quark on a kitchen scale. Instead, they use energy as their measuring stick. Here is the trick. Down at this tiny scale, weight and energy are 2 sides of the same coin. So instead of grams or ounces, physicists measure the mass of tiny particles using an energy unit. Do not worry about its full name. Just picture it as a special ruler built for the smallest things in the universe. On that ruler, the whole proton comes in at a certain number. Call it 1,000 marks. That is the mass every experiment agrees on. A proton, measured over and over in labs across the planet, always lands right around 1,000 marks on this special ruler. Solid, reliable, rock steady. Now the scientists needed the weight of a single quark on that same ruler. This was brutally hard. Quarks refuse to sit still and be measured. They can never be pulled out of a proton and studied alone, for reasons we will get to soon. So researchers had to be clever, using indirect tricks and mountains of data to pin down the numbers. After years of work, the answers came in, and they were tiny. The up quark, on that 1,000-mark ruler, weighs only about 2 marks. 2 out of 1,000. The down quark is a little heavier, weighing around 5 marks, still almost nothing compared to the full proton. Stop and let those sizes sink in. The proton sits at 1,000. The quarks inside it weigh 2, 2, and 5. On the scale of the whole proton, each quark is a crumb, a speck on a speck. Picture it this way. Imagine a school bus that weighs as much as a full-grown blue whale. Now imagine cracking open that bus and finding only 3 tiny paper clips inside. That is the size gap we are talking about. The container is monstrously heavier than the things it holds. This makes no sense in the everyday world. When you fill a backpack, the backpack ends up as heavy as the stuff you shoved into it. A bag of groceries weighs as much as the groceries. The container plus the contents, that is your total. Always. But the proton breaks that rule in the most extreme way possible. Its contents weigh almost nothing, while the proton itself is heavy. Somehow you can take a few nearly weightless crumbs, bind them together, and end up with something hundreds of times heavier than all the crumbs combined. If you did that with real objects, you would call it magic. Put a few grains of rice in a box, seal it, and the box suddenly weighs as much as a car. You would check for a trick. You would look for a hidden weight taped underneath. So that is exactly what physicists went looking for. A hidden weight. Some secret heavy thing buried inside the proton that they had missed. They searched. They measured. They checked every piece they could find, and when they finished counting up everything with actual weight inside the proton, the grand total still came out to almost nothing. The mystery only got worse. The proton weighs 1,000, its parts weigh about 9. So where are the other 991 marks hiding? Let us make the gap painfully clear, because this single fact is the entire heart of our story. Everything else tonight grows out of this one impossible number. Take the proton. On our special ruler it weighs 1,000 marks. That is the whole thing, the complete particle, measured by every lab on Earth. Now open it up and count the weight of its 3 quarks. Up quark, about 2. The other up quark, about 2. The down quark, about 5. Add them together. 2 plus 2 plus 5 gives you 9. 9 out of 1,000. So the 3 quarks, the actual building blocks of the proton, make up less than 1% of its weight. Less than 1 part in 100. If the whole proton were a $100 bill, the quarks inside it would be worth less than $1 single of that. Read that again. The parts that are supposed to build the proton account for barely 1% of it. The other 99% comes from something with no weight of its own. This is where your brain should be screaming. And this gap is rock solid. It has been checked and rechecked for decades with better and better tools. The answer never changes. The quarks are tiny, the proton is heavy, and 99% of that weight has no obvious source. Now bring it home to your own body. You're made of atoms. Those atoms get almost all their weight from protons and neutrons, and those protons and neutrons get 99% of their weight from something other than the quarks inside them. Step on a bathroom scale tomorrow morning, watch the number appear. Whatever it says, 99% of it has nothing to do with the actual chunks of matter in your body. The real matter, the quarks, would barely register. If your weight came only from the quarks inside you, you would weigh about as much as a small paperclip. Imagine that. Everything you think of as your physical self, all your solid flesh and bone, adds up to the weight of a paperclip once you strip away the mystery. The rest is something else entirely, something invisible, something that fills the space inside every proton in your body and gives you nearly all of your mass. For years, this drove physicists a little crazy. They had found the pieces of matter, they had measured them, and the pieces flat out failed to explain the thing they built. It was as if you took apart a heavy anvil, weighed every scrap of metal, and discovered the scraps weighed less than a feather. Where did the anvil's weight go? The missing 99% had to be real. You can feel it. It pushes down on the scale. It makes rocks heavy and gives planets their pull. This weight is doing real work in the universe every single second. Yet it hides inside a place smaller than we can picture, and it flows from a source that carries no weight on its own. To find that source, scientists had to stop thinking about the quarks as the answer. The quarks were a dead end. The real secret was in the space between them, in whatever was holding those 3 tiny specks together. And whatever was doing the holding turned out to be the strongest thing in all of creation. Picture a room full of the smartest physicists alive, all staring at the same impossible number. The proton weighs 1,000. Its parts weigh 9. Nobody could explain the missing amount. For a while, this was one of the great embarrassments of physics. They understood the pieces perfectly and still could not build the whole. So they started asking a different kind of question. Instead of hunting for a hidden heavy object, they asked what was going on in the space inside the proton. What was holding those 3 restless quarks together in the first place? Because quarks do not want to sit still. Left alone, they would fly apart instantly. Something has to grip them. Hard, every moment, or the proton would fall to pieces. That grip is a force, and forces, it turns out, are the key that unlocks the whole mystery. You already know some forces. Gravity is one. It pulls you down into your chair right now and keeps the moon circling the Earth. It feels powerful when you fall. But on the scale of tiny particles, gravity is almost a joke. It is by far the weakest force in nature. Between 2 quarks, gravity might as well not exist. Then there is the force that runs your whole life without you noticing. It lights up your phone screen, sparks in a lightning bolt, and holds the electrons inside every atom in place. Scientists call it electromagnetism. It is far stronger than gravity. It is the reason your hand does not pass straight through a table when you push on it. For a long time, those two seemed like the big players, but neither one could do the job inside the proton. Gravity is far too weak, and electromagnetism actually causes a problem. Two of the quarks in a proton carry the same kind of electric charge, and same charges push each other away hard. By that rule alone, the quarks should be blasting apart instead of clumping together. So something else must be in there. Something even stronger than the force that repels those quarks. Something powerful enough to overrule electromagnetism and pin the quarks in place inside a space almost too small to imagine. And whatever it has to be mighty. Remember, it is squeezing quarks together even while their electric charges are screaming at them to flee. It wins that fight easily, every single time, in every proton in the universe. That takes serious muscle. Scientists gave this mystery force a blunt, honest name. They called it the strong force, and the name fits perfectly. Inside the proton, the strong force is roughly 100 times mightier than electromagnetism. It is the undisputed champion of all the forces in nature. Nothing else even comes close. Here is the piece that changes everything. A force is a form of energy. When the strong force clamps down on those three quarks and holds them in place with unbelievable power, that clamping stores a massive amount of energy inside the proton. The harder the grip, the more energy is locked up in it. The proton is packed with this stored energy. It is crammed into every corner of that tiny space, buzzing and straining, holding the quarks captive, and that stored energy is the key, because a scientist with wild hair, decades earlier, had already written down the one equation that turns energy like this into weight. His name was Albert Einstein, and in the year 1905 he wrote down 5 symbols that would eventually explain your entire body weight. You have almost certainly seen them. E equals mc squared. Most people can recite that equation and have no idea what it truly says. So let us throw away the symbols and get to the real meaning, because it is one of the most shocking ideas humans have ever discovered. Einstein realized that mass and energy are the same thing, wearing 2 different outfits. Mass is simply energy that is holding still and bunched up. Energy is mass that has been set loose and freed. You can turn one into the other, like ice melting into water and freezing again. Before Einstein, everyone thought weight and energy were totally separate. Weight was the stuff, the heavy matter you could hold. Energy was the action, the heat and light and motion. 2 different worlds. Einstein tore down the wall between them and showed they were one. The c in his equation stands for the speed of light, the fastest anything can travel. And in the equation, that already huge number gets multiplied by itself, making it monstrous. What this tells you is powerful. A tiny amount of mass holds a gigantic amount of energy. Just a little matter can release an enormous burst of power. You have seen proof of this, even if you did not know it. The sun shines because of this equation. Deep in its core, it turns a small amount of its mass into light and heat every second, enough to warm a planet 93 million miles away. That is your morning sunlight, born from mass becoming energy. But tonight, we are running Einstein's idea in reverse, and this is where it gets beautiful. If mass can turn into energy, then energy can turn into mass. Pour enough energy into a small space, trap it there, and that trapped energy will start to behave exactly like weight. It will push down on a scale. It will resist being moved. It will act like solid matter, because at the deepest level it is the same thing as matter. Now go back to the proton. Remember what we just found inside it. The strong force is gripping 3 quarks with incredible power, and that grip stores a huge amount of energy in that tiny space. Energy that is trapped, buzzing, going nowhere. Do you see where this is heading? That trapped energy sitting inside the proton obeys Einstein's equation, and so it turns into mass. It becomes weight. Real weight. The kind you can measure. The kind that shows up on your bathroom scale. The energy of the strong force, locked inside the proton, becomes almost all of the proton's mass. That is the answer to our whole mystery. The missing 99% was never a hidden heavy object. It was energy all along. The energy of a force so strong it can be weighed. Your body weight then is mostly trapped energy, frozen into the shape of you by a force at war inside every proton. But to really believe that, we need to look at this force up close. We need to see the strange, invisible glue that carries it. let us go inside the proton and watch the strong force at work, because it behaves like nothing else in the universe, and its rules are so weird they sound made up. First, feel its raw power. The strong force is the strongest force there is. Inside the proton, it is about 100 times stronger than the electric force trying to blow the quarks apart. To picture that gap, imagine a tug of war. On one side, a couple of kids pulling on a rope. On the other side, 100 grown adults heaving with all their might. The kids are electromagnetism. The 100 adults are the strong force. The adults win in a landslide. This force is the reason atomic nuclei hold together at all. Cram several protons into a nucleus, and their electric charges should shove them apart with tremendous violence, yet they stay locked together. The strong force overpowers that shoving and keeps the nucleus whole. Without it, no nucleus could survive for even a flicker of time, and that means without the strong force there would be no atoms, no matter, no stars, no planets, no you. Every solid thing in existence owes its very being to this force, winning its endless fight inside every nucleus. Now here's the first bizarre rule, and it will bend your mind. The strong force does not weaken with distance in the normal way. Think about how every force you know behaves. Stand near a campfire and it feels hot. Walk away and the heat fades fast. Magnets pull hard when close and barely at all when far apart. Gravity too gets weaker the farther you drift. The rule of the everyday world is simple. More distance means less force. The strong force flips that rule upside down. When two quarks sit right next to each other, close together, the strong force between them is oddly gentle, almost relaxed. The quarks can jiggle around freely, like they are barely being held. But try to pull those two quarks apart and something wild happens. The farther you drag them from each other, the stronger the force pulling them back becomes. Move them a little apart, the grip tightens. Move them farther, it clamps down harder still. The force fights you more and more the more space you try to create. Picture stretching a rubber band. When it is loose, you feel almost nothing. But the more you pull, the more it strains and resists, yanking back against your fingers, wanting to snap the two ends together again. The strong force works like that rubber band, except it never stops getting stronger, no matter how far you stretch it. This backward behavior is the secret to the whole thing. It is why the quarks can never escape. It is why they stay trapped forever inside the proton. And, as we will see, it is why so much energy gets stored inside that tiny space, energy that becomes your weight. But a force needs something to carry it. The strong force has its own special particle, a courier that zips between the quarks, delivering the force over and over, billions of times faster than you can blink. Scientists gave this messenger a name that fits its job perfectly, and when you learn what this particle weighs, the mystery of your mass will take its strangest turn yet. The messenger of the strong force has a name that tells you exactly what it does. It is called a gluon, as in glue. It is the glue that holds the quarks together inside every proton in your body. Here is how it works. The strong force gets delivered, moment by moment, by these gluons flying back and forth between the quarks. Picture 3 players on a field, constantly throwing balls to each other, so fast the balls become a blur. Every throw is a tug that pulls the players together. The gluons are those balls, and there are floods of them, zipping between the quarks at unimaginable speed. The quarks are drowning in gluons. At any instant, a swarm of them is streaking through the proton, being thrown, caught, and thrown again in a non-stop storm of exchange. This furious back and forth is the strong force in action. It never pauses and never rests, roaring on through the entire life of the proton. Now here comes the fact that should stop you cold. The gluon has no mass. None. Zero. A gluon weighs absolutely nothing on its own, exactly like a particle of light. It is pure, weightless energy in motion. Let that land. The proton gets 99% of its weight from the strong force. The strong force is carried entirely by gluons, and gluons weigh nothing at all. So we have arrived at something that sounds flatly impossible. Almost all of your body weight is created by particles that themselves have no weight. Weightless things working together produce weight. It feels like a riddle with no answer, like building a brick wall out of shadows. But Einstein already told us how this can happen. Remember his equation: energy becomes mass. And the gluons, even though they weigh nothing, are absolutely bursting with energy. They are constantly flying at the speed of light, carrying the strongest force in nature between the quarks. All that motion, all that force, all that furious activity adds up to a colossal amount of energy trapped inside the proton. And by Einstein's rule, trapped energy is weight. So the weightless gluons, through their frenzy of energy, create almost all of the proton's mass. The glue weighs more than the things it glues because the gluing itself is packed with energy, and energy has weight. Think of it like a swarm of bees inside a sealed jar. Each single bee is light, but a whole swarm buzzing furiously carries real energy in all that motion. Now imagine that energy of motion was so intense it made the jar itself heavier. That is close to what is happening inside the proton, except the effect is far more extreme. The buzzing storm of gluons and quarks is so packed with energy that it becomes the bulk of the proton's mass. This is one of the deepest truths in all of physics. The solid world around you, the desk, the wall, your own hand, is built mostly from the trapped energy of weightless particles racing at light speed inside protons. Matter, at its foundation, is frozen motion. But the gluons hide another secret, one even stranger than being weightless. They carry a hidden property that comes in colours, and this property is what makes the strong force behave so unlike anything else in the universe. Every force in nature works by grabbing onto some special property that certain particles have. To understand the strong force, we need to find out what property the quarks and gluons are grabbing onto, and the answer is one of the strangest ideas in all of science. Start with a force you already know. Electricity works by grabbing onto a property called electric charge. Some particles have it, some do not. Charge comes in two flavours, which we call positive and negative. Opposite charges pull together, matching charges push apart. That simple rule runs all of electricity and magnetism. Two types of charge, and that is the whole game. The strong force plays a similar game, but with a twist that will make you smile. Quarks carry their own special kind of charge, a property that has nothing to do with electricity. It is a completely separate feature of the quark, one that only the strong force can feel. Scientists needed a name for it, and they made a fun choice. They called it colour. Now, this is important, so let me be clear. Quarks are not actually coloured. They are far too small to have any colour at all, since colour is just light bouncing off objects, and quarks are smaller than any wave of light. The name is a nickname, a label to help physicists keep track of things, but it is a clever nickname, and you will see why in a second. Electric charge came in two types. This strong force charge comes in three types, and scientists named those three types after the three colours that mix to make white light: red, green, and blue. Every quark inside a proton carries one of these three colour charges. One quark is red, one is green, one is blue. Here is why the nickname is so clever. In the real world, if you shine red, green, and blue light together, they blend into pure white. White is what you get when all three colours combine in balance. It is neutral, complete, settled. The strong force follows that exact same pattern. It insists that particles come together in balanced neutral combinations. A proton must contain one red quark, one green quark, and one blue quark, so that its colours add up to white. The proton is colour neutral, perfectly balanced, with all three colours present. The strong force will not allow anything else. It demands the full set. This rule of always balancing to white turns out to be a law of nature, and it is strict. You will never find a proton with two red quarks and no blue one. You will never find a lonely green quark drifting through space. The universe enforces colour balance everywhere, all the time, without exception. Everything made of quarks must add up to white, and the gluons, the glue particles, are tangled up in this colour game too. When a gluon flies from one quark to another, it actually carries colour with it, swapping the colours of the quarks as it goes. A quark might start red, throw a gluon, and turn blue, while the quark that catches it flips the other way. The colours are constantly changing, trading, shuffling, all to keep the proton balanced to white. This constant swapping is a storm of activity, and it leads to the single strangest feature of the strong force, a feature that light does not share, a feature that changes everything. To see how bizarre gluons truly are, we need to compare them to the messenger of a force you already know. Light itself is a messenger particle. When two electric charges push or pull on each other, they do it by tossing tiny bits of light back and forth. Those bits of light are called photons. The photon is to electricity what the gluon is to the strong force. Both are couriers, carrying a force between particles, but there is a giant difference between them, and it is the reason the strong force is so wild. Think about photons, the messengers of light. A photon carries the electric force, yet the photon itself has no electric charge. It is neutral. It delivers the message without being part of the message. This has a simple effect that you see every day. Two beams of light can cross right through each other and keep going untouched. Shine two flashlights so their beams overlap, and nothing happens where they meet. The photons ignore each other completely. They pass like ghosts. That is why light behaves so calmly. The messengers do not interfere with one another. They deliver their force and move on, minding their own business. Electricity is powerful, but its messengers are loners. Now look at the gluon and prepare for the twist. The gluon carries the strong force which grabs onto color charge. But unlike the well-behaved photon, the gluon carries color charge itself. The messenger is part of the message. The courier is also cargo. This one difference changes everything. Because the gluon carries color, gluons feel the strong force. They pull on each other. They grab each other. Two gluons that meet grab hold instead of passing by. They stick together and yank on one another with the same fierce power they use on quarks. Picture the difference. Photons are like polite messengers who hand you a letter and walk away, never bothering each other. Gluons are like messengers who grab every other messenger they pass, forming a giant tangled pile-up, all clinging together as they try to deliver their letters. That is what fills the inside of a proton. A snarled, seething tangle of gluons, all gripping each other, all pulling, all adding their energy to one enormous knotted mess. The gluons multiply the chaos. Every gluon can spawn more gluons, which grab still more gluons, in a runaway storm of grabbing and pulling, and here is why that matters so much for your weight. All that extra grabbing pours in even more energy. If gluons ignored each other like photons do, the proton would be a much calmer place, and it would weigh far less. But because gluons cling to each other, the energy inside the proton piles up to staggering levels. More grabbing means more energy. More energy, by Einstein's rule, means more mass. So this single strange feature, gluons grabbing gluons, is a huge reason the proton is so heavy. It is a huge reason you weigh what you weigh. The self-grabbing glue cranks the energy inside every proton up to a roar. This is also the key to the strangest behavior of all. Because gluons pull on each other, the strong force does something no other force in nature does. It gets stronger as things move apart, and that backward rule leads to a kind of prison that no quark can ever escape. Let us return to that backward rule because it is one of the most mind-bending facts in all of physics, and it grows straight out of the gluons grabbing each other. Every force you have ever felt gets weaker with distance. Move away from a fire and it cools. Pull a magnet off the fridge and its grip fades. Fly a rocket away from Earth and gravity loosens its hold. The whole world runs on this rule. Closer is stronger, farther is weaker. It feels like common sense because you have felt it your entire life. The strong force laughs at that rule. Inside the proton, it does the exact opposite, and this backward behavior is the beating heart of our whole story. When two quarks are close together, packed side by side, the strong force between them is surprisingly weak. It is so gentle, in fact, that the quarks can zip around almost freely, barely feeling the grip. Scientists have a name for this odd calm at close range. They call it asymptotic freedom, which is a fancy way of saying the quarks are nearly free when they are near each other. Do not worry about the term. Just picture two quarks close together, dancing around loosely, hardly held at all. Now start pulling those quarks apart. The moment you create some distance, the force wakes up and grows. Pull a little, and it tugs back. Pull farther, and it hauls harder. Keep pulling, and the strong force clamps down with more and more power, fighting you every inch of the way. The farther apart the quarks get, the more fiercely the force drags them back together. This is where the rubber band picture earns its keep. Grab a rubber band and hold it loose between two fingers. It just dangles there, floppy and relaxed. That is two quarks sitting close. Now stretch it. As you pull your fingers apart, you feel the band strain. tightening, pulling back harder the more you stretch it. That growing pull as you stretch is exactly how the strong force behaves between two quarks. But the strong force is even more extreme than any rubber band. A real rubber band eventually snaps and gives up. The strong force never quits. The farther you drag the quarks apart, the more energy you have to pour in, and there is no limit. Try to yank a quark clean out of a proton, and you find yourself fighting a force that only grows more savage the harder you pull. Think about what that means for the energy inside the proton. This growing tension is loaded with energy. Every bit of strain in that invisible rubber band is stored energy, coiled and waiting. And remember Einstein, stored energy is weight. So this straining, stretching, ever-tightening force is constantly pumping energy, and therefore mass, into the proton. The quarks live inside a web of these rubber band forces, all pulling, all straining, all packed with energy. That web is a huge part of why the proton weighs what it does. You are held together, right now, by countless invisible rubber bands strung between quarks, each one storing a piece of your weight. And this backward force does something almost unbelievable. It makes escape flat out impossible. Because if pulling a quark away only makes the force stronger, then no quark can ever break free. Try hard enough, and something shocking happens instead. The universe would rather create brand new matter than let a single quark escape alone. So let us actually try to do the impossible. Let us try to rip a single quark out of a proton and hold it in our hand, all by itself. Nobody in history has ever managed it, but walking through the attempt reveals something amazing about how the universe works. Grab a quark in your imagination and start pulling it away from its two partners. As you pull, that rubber band force we talked about starts to strain and tighten. You feel it fighting back. You pull harder, it pulls harder, pulls. You keep dragging the quark farther out, pouring more and more energy into the stretch, and the invisible band between it and the others grows tighter and hotter with stored energy. Here is the thing about stretching that band. All the energy you're pumping in has to go somewhere. It piles up in the stretched force between the quarks, building higher and higher, like water rising behind a dam. More pull, more energy, more strain. The band is now loaded with an enormous amount of energy, all crammed into that stretched space. And then, at some point, the universe reaches its breaking point and does something wild. Remember Einstein's rule, the one running through this whole story: energy can turn into mass. Well, you have now stuffed so much energy into that stretched band that the energy suddenly converts itself into new matter. Out of the pure energy of the stretch, a brand new quark pops into existence, along with its partner, an antiquark. Think about how strange that is. You are trying to pull one quark out. Instead of getting a lonely quark, the energy of your pulling created two fresh new particles out of nothing but stored force. It is as if you tried to separate two magnets, and the moment you pulled hard enough, two entirely new magnets appeared in the gap. Now the rubber band snaps at that new point, and the new quarks rush in to pair up. Your original quark grabs the new antiquark and forms a new little particle. The other partners grab the new quark, and so instead of one free quark in your hand, you end up with two complete particles, each with its colours balanced back to white. The universe rearranged itself to keep every quark bound. Picture snapping a bar magnet in half, hoping to get a single north pole all by itself. Instead, each broken piece instantly grows a new south pole, and you're left with two complete magnets, each with a north and a south. No matter how many times you snap, you never get a lonely pole. The quarks work the same way. Snap the band, and new quarks appear to keep everyone paired up. This is the reason nobody has ever seen a single, free quark drifting through space, not once in the entire history of science. The strong force simply will not allow it. Every attempt to isolate a quark just creates more quarks, all of them instantly bound into balanced groups. The lonely quark is forbidden. And notice the deeper lesson hiding here. When you pull hard, energy becomes matter. New mass appears out of stored force. That is Einstein's equation happening right in front of you, energy turning into weight, the very same process that fills the proton with mass. This trap has a name, and it seals the quarks inside their tiny prison for all of time. Scientists call this trap confinement. It is one of the deepest laws of the universe, and it means exactly what it sounds like. Quarks are confined, locked up, sentenced to spend their entire existence trapped inside particles like the proton, never once tasting freedom. Think about how total this imprisonment is. In everything else in the universe, you can take things apart. Break a rock and you get smaller rocks. Split a log and you get pieces of wood. Even the atom, once thought unbreakable, can be split apart, and its pieces can be pulled out and studied on their own. Scientists have held electrons alone. They have isolated all sorts of particles, but never a quark, not once. In every experiment ever run, across every lab on Earth, over more than 50 years of trying, no one has ever pulled a single quark out and held it by itself. The moment you try, as we just saw, the strong force conjures up new quarks to keep everyone paired. The prisoner can never walk out the door because the door creates new prisoners every time it opens. This makes the quark unique among all things we know. It is a piece of matter that can exist only in groups, never alone. A quark by itself is forbidden by the deepest rules of nature. The universe has decided that quarks travel in balanced teams, colours adding to white, and it enforces that decision without mercy, everywhere, always. So picture the proton now as a prison cell, one so small that 10 trillion of them would fit across a single hair. Inside sit 3 quarks, held captive by the strong force, unable to ever leave. They rush around their tiny cell at blistering speed, slamming again and again against invisible walls made of pure force, forever bound to each other, forever together. And here is the beautiful part. That imprisonment is the very reason you exist, the very reason you have any weight at all. Because the strong force is gripping those quarks so fiercely, holding them in that tiny space with such enormous power, it fills the proton with tremendous energy. The prison bars themselves are made of energy, and that energy, by Einstein's rule, becomes the mass of the proton, becomes your mass. Every ounce of you is built on this endless act of confinement happening in every proton in your body, trillions upon trillions of tiny prisons, each one crammed with the energy of quarks that can never escape. Your weight is the weight of that captivity. Now we're ready to look at the truth about what a proton really is, and it looks nothing like those 3 tidy circles from the textbook. That old picture, 3 calm little balls sitting quietly in a bag, was a comforting lie. The reality is far stranger and far more alive. Because when scientists learned to peer inside the proton with their finest tools, they did not find a peaceful little bundle. They found chaos, motion, a churning frenzy of activity so intense it barely seems like matter at all. To see that frenzy clearly, we first have to understand something shocking about empty space. Even the emptiest, most perfect vacuum with nothing in it whatsoever turns out to be secretly, wildly alive. Here is an idea that took physicists a long time to accept, and it sounds impossible at first. Even the emptiest space you can imagine is secretly boiling with energy and activity. A perfect vacuum, a region with every last speck of matter removed, still fizzes with hidden life. True nothingness, it turns out, cannot exist. Let me show you what this means. Imagine the emptiest place you can dream up, a sealed box, out in deep space, far from any star. Suck out all the air, all the dust, all the light, every single particle. What is left should be pure, silent, empty nothing. That is what everyone assumed for centuries, but the rules of the tiny world, the rules that govern particles and forces, say something wild. On the smallest scales, empty space cannot ever be truly still or truly empty. Instead, it fizzes, it bubbles, it crackles with tiny flickers of energy, appearing and vanishing so fast you could never catch them. The vacuum is like the surface of a boiling pot, constantly popping with little bubbles, except the bubbles are made of energy itself. Where do these flickers come from? They come from one of the strangest rules in nature. On the tiniest scales, energy is allowed to borrow against nothing for a brief instant. For a flash of time far shorter than you can imagine, a little bundle of energy can appear from the emptiness, exist for the tiniest moment, and then vanish again, paying back what it borrowed. This happens everywhere, all the time, in every corner of empty space. Sometimes that borrowed energy turns into particles. Following Einstein's rule once more, the flicker of energy becomes a pair of tiny particles, a matter particle and its opposite, that blink into being and then instantly wink back out, cancelling each other before the universe even notices. Physicists call these fleeting flashes virtual particles. They are the constant, restless bubbling of empty space. This is not some wild guess. Scientists have measured the effects of this bubbling vacuum in real experiments, and the numbers match perfectly. The emptiness really does churn with these appearing and vanishing flickers. It is one of the most solidly proven strange facts in all of physics. So even the most perfect emptiness is alive with energy, popping and fizzing forever. Now hold that thought, and shrink yourself back down into the proton. Because the inside of a proton is one of the busiest, most energy-soaked places in the entire universe. If empty space bubbles gently, the inside of a proton roars. Picture the difference. Ordinary empty space is like a calm pond with a few tiny bubbles rising now and then. The inside of a proton is like a raging whitewater rapid, churning and exploding with energy at every point. The strong force packed into that tiny space drives the bubbling to an absolute frenzy. Flickers of energy are turning into particles constantly, everywhere, all at once. And those flickers bring whole extra quarks along too. Down in that boiling storm they appear and vanish, blinking in and out of existence millions upon millions of times faster than you could ever blink your eyes. These ghostly, flickering quarks fill the proton alongside the three real ones. They come and go in an endless flurry, and they completely shatter the old idea of the proton as a simple bag holding just three little balls. Let us meet these ghost quarks, because they are one of the eeriest things hiding inside you right now. They flash into existence and then vanish so quickly that calling them real almost feels wrong. Yet they are there, filling every proton in your body, part of the churning storm that gives you weight. Remember the three quarks we started with? 2 ups and a down. Those 3 are the permanent residents of the proton. Physicists call them the valence quarks, the ones that truly define what the proton is. They are always there, the core team, but they are far from alone. Inside the boiling energy of the proton, that raging vacuum we just described, extra quarks are constantly popping into being. A quark and an anti-quark flash into existence, born from the energy of the strong force, live for the tiniest sliver of a moment, and then find each other and vanish again, cancelling out. Then another pair appears somewhere else, then another and another. Millions and millions of these flickers, over and over, without end. Scientists call these fleeting extras the sea quarks. It is a perfect name. The 3 valence quarks are like 3 swimmers, and around them churns a vast, restless sea of ghost quarks, appearing and disappearing like foam on crashing waves. The 3 real quarks are swimming in an ocean of their own flickering copies. So at any given instant, if you could freeze the proton and count what is inside, you would find a wild, shifting crowd. 3 permanent quarks, a swarm of gluons grabbing each other, and a boiling sea of ghost quarks flashing in and out everywhere you look. The count is never the same twice, because the sea is always changing, always churning. This completely destroys the old chalkboard drawing. The proton is a seething, roaring, ever-changing storm of particles, most of which flicker in and out of existence faster than thought. If you took 100 snapshots of the same proton, each one would look different, because the frenzy inside never holds still for even an instant. Picture a jar that looks like it holds 3 marbles, but when you shine a bright light through it, you see the whole jar is actually filled with a swirling mist, thick with countless tiny sparks flashing on and off, and the 3 marbles are lost somewhere in the storm. That mist, that endless flashing, that is the true inside of a proton. And every one of those flickers cost energy. Every ghost quark that pops into being, every gluon grabbing another gluon, every strain in every rubber band of force, all of it is loaded with energy. And by Einstein's rule, running quietly beneath this entire story, all that energy becomes mass, becomes weight, becomes you. So your weight is alive with motion inside you. It is a storm. Right now, inside every proton in your body, this frenzy is raging, trillions of tiny tempests churning at once, and the total energy of all that churning is what pins the needle on your bathroom scale. We are finally ready to see the whole picture at once, the real proton in all its violent glory, and to understand why the calm little ball of the textbooks was never real at all. Let us step back and look at the whole proton at once, seeing it clearly for the first time, the way modern physics actually understands it. Forget the three tidy circles forever. The truth is wilder and more alive than anyone first imagined. Zoom into the proton and here is what you find. Three real quarks, the up, and down, rushing around at blistering speed. Between them and around them, a furious storm of gluons, each one grabbing other gluons, tangling together into a seething knot of force, and filling every gap, a boiling sea of ghost quarks, flashing into being and vanishing again millions of times faster than you can blink. All of it churning, colliding, exchanging, transforming, without a single moment of rest. This is the most violent, energy-packed environment in the known universe, crammed into a space so small that 10 trillion of them would fit across one strand of your hair. Inside that unimaginably tiny volume, a storm rages that never ever calms. The word calm never applied to the proton at all. From the moment it formed, near the very birth of the universe, this storm has been raging inside it. And it will keep raging for longer than you can picture, quite possibly for the entire future life of the cosmos. The proton is one of the most stable things in existence, and yet inside, it is pure chaos, held in perfect balance. Think about what that really means. The chair you're sitting on feels rock solid and still, but every proton inside it holds a roaring tempest. The table, the walls, your own hand, all of it looks calm and frozen on the outside, while inside every single proton, an unimaginable frenzy churns without pause. Solid matter is a lie, your senses tell you. Underneath, everything is storm, and now we can finally answer the question we started with. Where does the proton's weight come from? It comes from the storm. The three quarks, remember, barely weigh anything. Less than 1% of the proton. All the rest, the missing 99%, comes from the energy of this raging storm, the energy of the gluons grabbing each other, the energy of the ghost quarks flashing in and out, the energy of the quarks racing around, the energy stored in every straining rubber band of force. Add up all that energy, apply Einstein's rule, and you get almost the entire weight of the proton. The storm is the weight, the frenzy is the mass. What feels like solid, heavy matter is really trapped energy in furious motion, frozen into a shape by a force that never lets go. So when you feel your own weight pressing into your chair, you are feeling storms. Trillions upon trillions of tiny tempests raging inside the protons that make you, their energy adding up, pressing down, becoming the number on the scale. You are, in a very real sense, made of frozen storms. There is one more piece to this puzzle that we have only touched on lightly, and it may be the most staggering of all. The quarks inside this storm are not drifting lazily, they are moving, racing in fact at speeds so close to the speed of light that the numbers barely seem believable. And that blistering motion stores an incredible amount of energy all on its own, energy that becomes yet another huge chunk of your weight. Let us focus on the speed of those three quarks, because it is one of the most jaw-dropping facts in this entire story, and it reveals the final major source of your weight. The quarks inside a proton move at a staggering pace. They race around their tiny prison at speeds so close to the speed of light that it is hard to put into words. The speed of light is the ultimate cosmic speed limit, the fastest anything in the universe can possibly go, about 670 million miles per hour. The quarks come astonishingly close to that limit, blazing around inside the proton at a huge fraction of the fastest speed there is. Now think about what happens when things move fast. Motion is energy. A moving object always carries energy just because it is moving, and the faster it goes, the more energy it holds. A thrown baseball carries more energy than a gently rolled one. A speeding car carries far more energy than a parked one. This energy of motion is real, as anyone who's been hit by a fastball can tell you. Now crank that idea up to the extreme. The quarks are moving at nearly the speed of light, the most extreme motion possible. So each quark carries an absolutely enormous amount of energy of motion, packed into its blistering race around the proton. It is the fastest movement matter can achieve, and it stores energy to match. And you already know where this is heading. Energy of motion is still energy, and by Einstein's rule, the one running through every part of this story, energy becomes mass. So the raw speed of the quarks, their frantic light speed racing, gets converted straight into weight. The faster they move, the more they weigh, even though the quarks themselves are nearly massless when standing still. Picture it this way. Imagine a marble that weighs almost nothing when it sits on a table. Now imagine spinning that marble so impossibly fast that its sheer speed made it heavy, so heavy you could feel it pressing down. That is close to what is happening with the quarks. Their motion is giving them heft, far more than their matter ever could. So now we can gather up all the sources of the proton's weight and see them together. There is the energy of the gluons grabbing each other. There is the energy stored in the straining rubber bands of the strong force. There is the energy of the boiling sea of ghost quarks. And now, on top of all of it, there is the tremendous energy of the three real quarks racing around at nearly the speed of light. Every one of these is energy, and by Einstein's rule, energy becomes mass. Stack all that energy together and it accounts for almost the entire weight of the proton. The tiny bit of true resting matter in those three quarks contributes barely a whisper. Everything else, the vast bulk of what makes you heavy, is energy in furious motion, frozen into the form of a proton. This means your body weight is mostly stored motion and stored force. You are, at your very foundation, energy caught in a trap, spinning and straining and roaring inside countless tiny prisons. But knowing all this, and proving it are two different things, how could anyone ever show that a storm of invisible energy adds up to the exact weight of a proton? The answer would take some of the most powerful machines humans have ever built. Before we watch scientists prove it with their machines, let us make the whole answer crystal clear, because it is one of the strangest truths about your own body. Here is everything we have found, gathered into a single picture. A proton weighs 1,000 marks on our special ruler. The three quarks inside it weigh about 9. So where do the other 991 come from? They come from energy. The energy of the strong force gripping the quarks, the energy of the gluons grabbing each other, the energy of the ghost quarks boiling in and out of the storm, the energy of the real quarks racing at nearly the speed of light. Gather all of that energy together, run it through Einstein's rule, and it turns into mass. That mass is the missing 99%. Say it plainly. The proton is heavy because it is packed with trapped energy. The energy is the weight. There is no hidden heavy object buried inside. There never was. The heaviness pours out of motion and force, frozen in place by a prison the quarks can never leave. And here is where this stops being about tiny particles and starts being about you. Your body is built from atoms. Those atoms draw almost all their weight from protons and neutrons, and those protons and neutrons draw 99% of their weight from trapped energy. Follow that chain all the way down, and here is what waits at the bottom. Almost all of your body weight is energy, bound up energy, humming inside trillions of tiny storms, pressing down on the scale under your feet. Think about that the next time you feel heavy. When you hug someone you love, the warmth and the weight of them is mostly energy tied into knots. Pull away the trapped energy, and the actual solid matter in a grown adult would weigh about as much as a couple of raindrops. You are, at the deepest level, a pattern of frozen energy shaped like a person. Solid to the touch, warm in a hug, and built almost entirely from something that carries no weight of its own until the strong force clamps down on it. This is one of the most beautiful ideas in all of science. Mass, the very thing that makes you feel real and solid, is mostly just energy that got caught. The wall between matter and energy, the wall everyone believed was so tall and so clear, turns out to be no wall at all. They are the same stuff, and inside every proton in your body, energy is quietly playing the role of matter, and playing it perfectly. For a long time, this was a stunning idea carrying a serious problem. It was a story that made sense, that fit the math, that felt right in the gut. But feeling right and being proven are worlds apart in science. Nobody had ever actually shown that all this swirling energy adds up to exactly the weight of a proton, and proving it looked close to impossible. You cannot pry a proton open and lay its energy out on a table. You cannot freeze the storm inside and weigh each piece by hand. The whole thing unfolds in a space too small to enter, at speeds too fast to follow, with particles that vanish before you can grab them. So how do you check the answer? Scientists found a way, and it meant building a proton from scratch, out of nothing but rules and raw computing power. Here was the bold idea. If you cannot open a proton and measure the energy inside, then calculate it instead. Take the rules of the strong force, the laws that govern quarks and gluons, and use them to work out from pure math how heavy a proton should be. If the math spits out the same number the experiments measure, then the whole story of energy becoming mass would stand proven. Simple to say, brutal to do. The trouble is that the math of the strong force is some of the hardest math in all of physics. Remember what is happening inside a proton. 3 quarks racing around, a storm of gluons grabbing each other, a boiling sea of ghost quarks flashing in and out. Every one of those pieces pulls on every other piece, all at once, every instant. To calculate the total, you have to track all of it together. Tangled and endless. Here is the crushing part. In easier corners of physics, scientists have neat tricks to solve their equations, shortcuts that turn a nightmare into something a person can handle with paper and a pencil. Those tricks work when a force is gentle and the pieces mostly ignore each other. But the strong force is savage, and its pieces grab each other constantly. Every shortcut breaks, every clever trick falls apart. The equations refuse to be solved by hand. They are simply too tangled, with too many things affecting too many other things. For years, this stopped physicists cold. They had the rules written down. They believed the rules were right. Yet they could not use those rules to calculate the one number that would prove everything. The weight of a single proton. The answer was locked inside math too hard for any human mind to crack. So they turned to a different kind of mind. A machine that never gets tired, never makes a careless slip, and can crunch numbers at a speed no person could ever match. They turned to the supercomputer. A supercomputer is not like the laptop on your desk. It is a monster. Picture a room the size of a basketball court, packed wall to wall with humming machines, all wired together to work as one gigantic brain. The most powerful of these machines can perform more calculations in a single second than there are grains of sand on a long stretch of beach. They gulp down enough electricity to power a small town. They run so hot they need rivers of cooling water just to keep from melting. These machines are among the rarest and most costly tools on the planet, and only a handful of them exist anywhere on Earth. This was the tool that might finally crack the proton. The plan was to feed the rules of the strong force into one of these giant machines and let it grind through the impossible math, step by step for months on end, until it coughed up an answer. But even a supercomputer cannot solve the tangled equations directly. Nobody knows how. So scientists had to invent a clever way to break the problem into bite-sized pieces the machine could actually chew. Their method was strange and brilliant, and it started with a wild idea. They would take smooth, empty space and chop it up into a grid, like slicing reality itself into tiny cubes. The method they invented has a name that sounds almost cozy. They call it the lattice. And the idea behind it is genuinely clever, so let me show you how it works, because it is one of the great tricks of modern science. Real space is smooth. You can move through it however you like, in any direction, by any tiny amount. There are no steps, no edges, no grid. That smoothness is beautiful, but it is a curse for a computer, because smooth space holds endless points inside it, and no machine can handle endless. So the scientists cheated, in the smartest way. Instead of smooth space, they built a fake space made of a grid. Picture graph paper, but in 3 dimensions, a giant cube filled with evenly spaced dots, row after row, layer after layer. The quarks are only allowed to sit on those dots. The gluons only travel along the lines connecting them. Smooth reality gets replaced by a neat, countable grid of points. Think of how a photo on your phone works. Zoom in far enough, and the smooth image breaks into tiny squares of colour called pixels. Each pixel is one small block, and together they build a picture your eye reads as smooth. The lattice does the same thing to space itself, turning the flowing, endless proton into a picture made of countable dots, something a computer can finally handle. With space chopped into a grid, the impossible math becomes merely gigantic. The computer can now go dot by dot, working out what the quarks and gluons are doing at every single point, following the rules of the strong force one step at a time. It still takes an enormous number of steps, trillions upon trillions of little calculations all feeding into each other, but now at last the machine can actually do it. The scientists set up their grid, loaded in the rules, and let the supercomputer loose, and then they waited. This was slow. The machine churned through the calculations for months, running day and night without pause, chewing through more math than every human who ever lived could finish in 1,000 lifetimes. Somewhere in a cooled room, the giant brain hummed and worked, rebuilding a proton from nothing but rules and dots. Here is what makes this so powerful. The scientists did not tell the computer what a proton weighs. They never fed it the answer. They only gave it the rules of the strong force, the laws describing how quarks and gluons pull and grab and dance. Then they asked the machine a single question. Given these rules and nothing else, how heavy does a proton come out to be? If the story of energy becoming mass was true, the computer should build a proton where the trapped energy of the storm adds up to the full weight, all 99% of it, plus the tiny sliver from the quarks themselves. The machine would grind through the storm and hand back a number, and that number would settle everything. If it matched the weight measured in real labs, then the whole idea would be proven, straight from the fundamental rules of nature. If it came out wrong, the beautiful story would collapse, and physicists would have to start over. So the world's finest minds fed the rules into the machine and held their breath. After months of grinding, the supercomputer finally finished. It printed its answer. And what it revealed would go down as one of the great triumphs in the history of physics. The year was 2008. A team of scientists had spent years setting up the calculation, and the supercomputers had spent months grinding through it. Finally, the answer came out. They compared the weight the computer had built, using nothing but the rules of the strong force, against the weight measured in real laboratories. The two numbers matched. Not roughly, not in the ballpark. They matched almost perfectly, agreeing to within a tiny margin, close enough to leave no room for doubt. The proton the computer built from pure rules weighed the same as the proton nature actually makes. The trapped energy of the storm, calculated dot by dot across the lattice, added up to the exact heaviness that shows up on lab instruments around the world. Sit with what that means. Scientists took the raw laws of the strong force. They fed them into a machine. They never told the machine the answer. And out came a proton with the correct weight, 99% of it built from the energy of gluons and racing quarks, exactly as the story predicted. The idea had passed the hardest test imaginable. Picture an archer standing miles from a target, so far away the bullseye is invisible to the naked eye. She cannot see where she's aiming. She only knows the rules of the wind and the arrow. She lets fly, blind, trusting the math, and the arrow lands dead center. That is what the supercomputer pulled off. Working blind from rules alone, it hit the exact weight of the proton on the very first honest try. This was a monumental moment. For decades, the idea that mass comes from trapped energy had been a gorgeous story with a hole in it, unproven at the deepest level. Now the hole was filled. The calculation stood as hard proof that the strong force and the energy it stores really does create almost all the mass of ordinary matter, really does create almost all of you. It also proved that our rules for the strong force were correct. Think about how remarkable that is. Human beings, staring at the tiniest specks in existence, had written down a set of laws so accurate that a machine could use them to rebuild a proton from scratch and get the weight right. We had truly cracked the code of one of nature's deepest forces, and this confirmation runs deep, tested and retested by different teams using different machines, all landing on the same result. This is settled ground now, some of the firmest footing in all of physics. When scientists say your weight comes mostly from trapped energy, they are not guessing. They have built the proof, dot by dot, inside the most powerful machines humanity has ever made. So the mystery we started with, the impossible gap between the light quarks and the heavy proton, is a mystery no more. It is solved. The answer is energy, locked down by the strongest force in nature, and we have proven it beyond serious doubt. Yet a solved mystery always opens a door to deeper questions. We keep talking about the rules of the strong force as if they are some ancient scroll. But what exactly are these rules? Who wrote them down? They have a name. one of the strangest and most colourful names in all of science, and the story of how humans discovered them is a tale of two young scientists who stumbled onto something nobody expected. The rules of the strong force, the laws the supercomputer used to rebuild a proton, have an official name. Scientists call it quantum chromodynamics. It is a mouthful, so let us break it apart because each piece tells you something real. The word quantum simply means we are down in the tiny world, the strange realm of the smallest particles, where the everyday rules of your life stop working. The word dynamics just means motion and force, how things push and pull and move. And the middle piece, chromo, is the fun one. Chromo comes from an old word for colour, so the whole name means, roughly, the rules of colour force in the tiny world. There is that word colour again. Remember the hidden charge the quarks carry, the property that comes in red, green and blue, the thing the strong force grabs onto. This entire theory is built around that colour charge. That is why physicists baked the word right into the name. Most people shorten the whole mouthful to 3 letters and just call it the colour rulebook of nature. Here is what makes this rulebook so astonishing. It is a fairly small set of laws. You could write the core ideas on a single sheet of paper, yet from those few rules pours all the wild complexity we have explored. The gripping of the quarks, the gluons grabbing gluons, the backward force that grows with distance, the prison of confinement, the boiling sea of ghost quarks, the storm that creates your mass. All of it flows out of this one compact rulebook, like an entire forest growing from a handful of seeds. Think of it like the rules of a board game. A game like chess has only a few simple laws. This piece moves this way, that piece moves that way. Yet from those few rules come billions of possible games, dazzling strategies, moments of genius no one could have predicted. The colour rulebook works the same way. A few tight laws, and out of them explodes the entire rich behaviour of everything inside a proton. And this rulebook does more than explain the proton. It governs the neutron too, and every particle built from quarks, and the way atomic nuclei hold together it all. It is one of the crown jewels of human knowledge, a set of rules so powerful and so accurate that it describes a whole layer of reality with stunning precision. When the supercomputer rebuilt the proton, this rulebook was the recipe it followed, and the recipe turned out to be exactly right. But rulebooks do not write themselves. Somewhere, some human being had to figure these laws out, staring at confusing data, chasing a pattern nobody else could see. And the strangest, most important rule in the whole book, the backward force that grows with distance, was almost impossible to believe when it was first discovered. In fact, when 2 young physicists first found it in their equations, it seemed so wrong, so opposite to how every other force behaves, that they could hardly trust their own math. They had stumbled onto the secret that makes the strong force strong, the very rule that locks the quarks in their prison and fills the proton with mass, and their discovery would earn them a trip to collect the highest prize in all of science. Travel back to the early 1970s. At Princeton University, a professor named David Gross was working with a young student named Frank Wilczek. Gross was determined to understand the strong force, and honestly, he expected to prove that the current ideas about it were doomed. He set his brilliant student to work on the math, fully believing they would find the theory falling apart. Instead, they found the opposite. As they worked through the tangled equations, a shocking result appeared. The strong force, their math said, should grow weaker when quarks are close together and stronger when they are pulled apart. That was the backward behaviour, the exact rule we have followed through this whole story, and it was the reverse of what everyone assumed. At the very same time, at Harvard University, a graduate student named David Politzer was chasing the same math on his own. And he found the same startling answer. 2 separate groups working apart had both uncovered the strange secret of the strong force in the same short stretch of time. At first, the results seemed too weird to be real. Every force people knew grew weaker with distance. This one did the reverse. It was the kind of answer that makes a scientist check the math again and again, certain there must be a mistake hiding somewhere. But the mistake never turned up. The math was solid. The strong force truly does work backward. This discovery cracked the whole puzzle wide open. It explained why quarks can never escape. It explained the prison of confinement. It explained why the force can store such enormous energy, the energy that becomes your mass. This one strange rule was the missing key that made the entire colour rulebook finally make sense. Without it, nothing about the proton added up. With it, everything clicked into place. They gave the odd behaviour a name. They called it asymptotic freedom, that fancy term meaning the quarks roam nearly free when they huddle close together. Do not let the big words fool you. The idea is simple, and it is one of the most important ideas ever found about how matter holds itself together. For their discovery, David Gross, Frank Wilczek, and David Politzer shared the Nobel Prize in Physics in the year 2004, the highest honour a scientist can receive. The teacher and his student, along with the lone young researcher from Harvard, stood together and accepted the crown of the scientific world, all for finding a single rule that runs backward. Their work is the reason we can say, with confidence, where your weight comes from. It is the reason the supercomputer had the right rules to feed in. Three curious minds, chasing an answer they did not expect, handed humanity the key to understanding the mass of nearly everything. So the picture now feels complete. The strong force stores energy. That energy becomes mass. The rulebook is proven. The math is confirmed. The prize has been awarded. You would think the story of where your weight comes from is fully closed. But there is another famous idea about mass out there, one you have almost certainly heard of. It has been called the God particle. It made headlines around the world. Most people are told it is the thing that gives everything its mass. And now we have to face it, because the truth about that famous particle will surprise you. You have probably heard of it. It made front-page news around the world in the year 2012. Newspapers called it the God particle, a nickname most scientists dislike, but one that stuck. Its real name is the Higgs, and when scientists finally found proof of it, using the largest machine ever built, the whole world celebrated. People who had never taken a physics class suddenly knew the word, and the message everyone heard was simple. The Higgs is the thing that gives everything its mass. That single sentence ran in headlines everywhere. So let us understand what the Higgs actually is, and then face the surprising truth about how much of your weight it really explains. Picture the entire universe as being soaked in an invisible field, a kind of unseen ocean that fills all of space. This ocean is everywhere, in the room around you, out in deep space inside your own body. Scientists call it the Higgs field. You cannot see it or feel it directly, but it is always there, humming in the background of reality. Now here is the clever part. As certain particles travel through this invisible ocean, the ocean tugs on them, slowing them down, making them harder to push around. And being hard to push around is exactly what having mass means. The more a particle interacts with the Higgs field, the more the field drags on it, and the more mass that particle has. Picture wading across a swimming pool. In open air, you can wave your arm quickly and freely. But push that same arm through water, and it feels heavy and slow because the water pulls against it. The Higgs field works something like that pool. Particles that barely touch it slip through easily and stay light. Particles that grab onto it hard get dragged, and that drag shows up as mass. This is a real and confirmed piece of nature. The Higgs field exists. Scientists proved it by finding its matching particle, the Higgs boson, in that giant machine in 2012. It was one of the greatest discoveries in the history of science, the final missing piece of our deepest theory of particles. Peter Higgs, who first dreamed up the idea decades earlier, lived to see it proven and received a Nobel Prize of his own. So the Higgs is real, and it truly does give mass to particles. That part of the famous headline is correct. The quarks inside you, the electrons in your atoms, they get their own small mass from wading through this invisible Higgs ocean. Without the Higgs field, those tiny particles would have no mass at all, and they would rocket around at the speed of the light, unable to ever settle down into atoms. So the Higgs matters. It matters a great deal. Reality as we know it depends on it. The story you heard on the news held a real piece of the truth, but it was badly incomplete. Because there is a huge and surprising gap between what most people believe about the Higgs and what it actually does for your body weight. The headlines made it sound like the Higgs is the source of your mass, the reason your bathroom scale reads what it reads. And when you look closely at the numbers, that turns out to be almost entirely false. Here comes the twist that most people never hear, even though the Higgs made headlines everywhere. The Higgs field does give mass to the quarks inside you. That is true. But watch closely how much mass it gives, because the amount is shockingly small. Remember the numbers from the start of our story. The whole proton weighs 1,000 marks on our special ruler. The 3 quarks inside it weigh only about 9 of those marks. And here is the key. That tiny 9, the mass of the quarks themselves, is the part that comes from the Higgs field. The Higgs gives the quarks their little bit of resting mass, and that bit adds up to about 9 marks out of 1,000. 9 out of 1,000. That is the Higgs contribution to a proton, less than 1%. The famous particle, the one the whole world celebrated, the one people call the source of all mass, is responsible for barely a scrap of the proton's weight. Where does the other 99% come from? You already know. It comes from the strong force, from all that trapped energy of the storm we have explored. The Higgs handles the tiny sliver. The strong force handles the giant remainder. The celebrity gets 1%. The unsung hero gets the rest. Picture a pizza sliced into 100 pieces. The Higgs field is responsible for less than one single slice. The strong force storing energy inside the proton provides the other 99 slices. If you were paying for the pizza of your body weight, you would hand almost all your money to the strong force and drop a single coin in the Higgs jar. This flips the popular story completely. The headlines told the world that the Higgs gives everything its mass. But for the mass you actually carry around, the weight of your bones and blood and muscle, the Higgs is a bit player. It supplies a whisper. The strong force supplies the roar. Now, to be fair to the Higgs, it plays a role that matters more than its small size suggests. That tiny resting mass it hands the quarks is still important, because it helps set the exact properties of matter, and it makes the up quark and the down quark slightly different from each other. Those small differences turn out to matter a great deal for building a stable universe, as we will see soon. So the Higgs is small in weight, but not small in importance. Still, when it comes to the raw number on your scale, the verdict is clear, and it is stunning. The Higgs field, the God particle, the star of the headlines, accounts for about 1% of your body weight. Almost everything you weigh has nothing to do with the most famous mass particle in the world. Think about how strange that is. For years, people walked around believing the Higgs was the reason they had weight at all. Teachers said it, news anchors repeated it, and the whole time, the real source of nearly all human mass was a different thing entirely, a force most people have never even heard of, working silently inside every proton in every body on Earth. So the famous particle turns out to be almost a footnote in the story of your weight, which raises a question that reshapes how you should see yourself. If the Higgs barely counts, then what truly is the source of you? For years, the whole world walked around believing something about mass that turns out to be almost entirely wrong. Ask most people what gives their body its weight, and the ones who know a little science will point to the Higgs. It is the answer that filled the headlines. It is the answer in countless articles and classroom lectures. And for the weight you actually carry around, that answer misses the mark by a mile. We just saw the numbers. The Higgs field gives the quarks their tiny resting mass, and that adds up to about 1% of a proton. 1%. The most famous particle in the world, the so-called God particle, the star of a global celebration, turns out to be a bit player in the story of your weight. Sit with how strange that is. When scientists announced they had found the Higgs, it was front-page news on every continent. People who had never thought about physics for a single day suddenly heard that this particle was the reason everything has mass, the reason you have mass. Overnight, a strange word from the world of physics became a household name, printed on magazine covers and spoken on the evening news. It felt like humanity had finally found the source of heaviness itself. And the whole time, that story was mostly a mirage. The Higgs does its small job faithfully, handing out a whisper of mass to the fundamental particles. But the giant bulk of your weight, the 99%, was pouring out of a place the headlines barely mentioned. The famous particle earned its celebration for other reasons, while nearly all of your weight came from a source almost nobody was talking about. Think about what that means for how you have pictured yourself. If you ever learned that the Higgs gives you mass, you were handed a fact that is technically true and deeply misleading at the very same time. Yes, the The Higgs touches your mass, but it touches only the thinnest sliver. You could erase the Higgs contribution entirely and your weight would barely twitch, dropping by about 1 part in 100. Believing the Higgs is why you are heavy is like believing a single drop of water is why the ocean is deep. This is one of those moments where science quietly corrects a story that almost everyone believes, and this correction flips the whole picture. The particle we crowned as the king of mass is closer to a distant cousin who appears in 1% of the family portrait. The true ruler of your weight was never in the headlines at all. There is even a certain unfairness to it. The Higgs took decades to find, cost billions of dollars, demanded the largest machine humans have ever built, and earned a Nobel Prize. It richly deserves its place in history, yet for all its fame and all its cost, its job in your body is quiet and small. For the plain question of why your bathroom scale reads what it reads, the Higgs is almost beside the point. So we are left with a gap in the story, a question hanging in the air. If the famous Higgs supplies barely 1% of your weight, then something else must be supplying the other 99. Something powerful, something that has been hiding in plain sight this whole time, running the entire show without collecting any of the credit. You already know its name, and now it is finally time to give that force its due. Say it plainly, once and for all, the thing that gives you almost all your weight is the strong force. It grips the quarks inside every proton with staggering power. It fills that unimaginably tiny space with a roaring storm of energy. And by Einstein's rule, that energy becomes the mass that makes up nearly all of you. Step on a scale, and you're mostly measuring the strong force at work inside trillions of protons. This is the quiet hero of your existence. The Higgs got the headlines and the flashy nickname, while the strong force does the heavy lifting without a single newspaper story. Inside every atom of every living thing and every object that has ever been. It has been building your weight your whole life, and everyone else's, silently and faithfully, never once asking for the credit. Most people who feel their own weight every single day have lived and died without ever hearing its name spoken aloud. It is the greatest force you were never taught about in school. Picture a famous movie star whose face is on every poster, who takes top billing and a fortune, yet who appears on screen for only a few short seconds. Meanwhile, a background actor, one whose name you will never learn, fills nearly every scene and carries the whole film on their shoulders. The Higgs is the star with the tiny cameo. The strong force is the background actor holding the entire movie together, unseen and unthanked. Let this change how you see your own body. Picture what you're truly made of. Mostly trapped energy, held in place by a force. The solid bits you always imagined are only a tiny whisper of the whole. Your bones, your blood, your muscle, your beating heart weigh what they weigh because the strong force has locked enormous energy inside every proton you are built from. You are heaviness born from force. There is something almost beautiful in how hidden this was. The most important source of mass in your body is a force that most people have never heard of, working in a place far too small to ever see, following rules that humans only cracked a few decades ago. The grandest fact about your weight waited in the last place anyone thought to look, inside a speck 1 trillion times smaller than a single grain of sand. Once you truly feel this, it settles into a kind of wonder. Every pound of you is a monument to the strong force. Every step you take, every time you sink into a soft bed at the end of a long day, you're feeling the weight of captured energy, tamed and bound by nature's mightiest force. It is happening right now as you listen, in more places inside you than you could count in 100 lifetimes. Your very heaviness is proof of the storm raging within. But here is the part that makes it enormous. The strong force plays this exact same game inside every proton in existence, everywhere far beyond human bodies. Which means the truth about your weight is also the truth about your chair, the ground, the mountains and the sun. The whole solid world around you is stranger than it appears, and once you understand the proton, you can never see that world the same way again. Look around the room you're in. Every solid object you can see is playing the same trick your body plays. The chair holding you up, the floor under your feet, the walls around you, the phone or screen in front of you. Weigh any of them, and almost all of that weight is trapped energy, locked inside protons by the strong force. Take your chair. It feels heavy and solid and completely still. but nearly all of its weight comes from the same roaring storms we have explored, trillions of tiny tempests raging inside the protons that make up the wood, or metal or plastic. The chair is mostly frozen energy, shaped like a chair, holding you off the ground. The actual matter in it, the true resting mass of all its quarks, would weigh almost nothing on its own. Now step outside and look at the ground. The entire Earth, all of it, from the dirt under your shoes to the molten core thousands of miles down, gets almost all its weight the same way. A whole planet's 6 trillion pounds of rock and metal and water is mostly trapped energy held together by the strong force. If you could somehow strip that energy away and weigh only the raw matter of the quarks, the Earth would shrink to a tiny fraction of its heaviness. This idea keeps scaling up, and it only gets more staggering. Look up at the Sun. Our star is a giant ball of mostly hydrogen, and hydrogen is the simplest atom there is, built around a single proton at its heart. So the Sun is, in a very real sense, a colossal cloud of protons, more of them than you could count in 1,000 lifetimes, and each of those protons gets 99% of its weight from trapped energy. The Sun, the thing that lights our days and holds our planet in orbit, is mostly energy pretending to be matter. Picture that for a moment. The blazing ball in the sky, so massive it could swallow more than 1,000,000 Earths, owes almost all of its enormous weight to the strong force gripping quarks inside countless protons. Every sunrise you have ever seen is the glow of an object made mostly of captured energy. This is the deep truth hiding behind the solid, weighty world you live in. The heaviness of things, the very quality that makes matter feel real and substantial, is mostly an illusion of trapped energy. What you think of as solid stuff is, at its foundation, a pattern of energy locked into shape by the strongest force in nature. It does something to your sense of reality when this really lands. The line between energy and matter, the line that seems so obvious in daily life, simply does not exist down where it counts. Everything heavy is mostly frozen force. Everything solid is mostly caught energy. The universe of objects around you is a universe of storms, each one held perfectly still on the outside while raging within. And this reaches nearly the whole cosmos. The strong force is doing this everywhere, inside every proton and neutron in existence, which means the vast bulk of all the mass we can see in the entire universe comes from this single source. Let us go all the way out now, past the Earth, past the Sun, past everything, and ask the biggest version of the question: where does the weight of the whole universe come from? Everything we can see out there is made of the same basic stuff: stars, planets, moons, comets, giant clouds of gas, entire galaxies spinning with hundreds of billions of stars. All of it is built from atoms, and atoms, as we know by now, get almost all their weight from the protons and neutrons in their cores. So the weight of the visible universe is really the weight of an unthinkable number of protons and neutrons, and every single one of those protons and neutrons gets about 99% of its weight, from the strong force, from trapped energy, from the storm inside. Which leads to a jaw-dropping conclusion. Nearly all the mass of the entire visible universe, all the stars and planets and galaxies we can see, comes from this one force, from energy locked down by the strong force inside countless tiny particles. Try to picture the scale. There are more stars in the observable universe than there are grains of sand on every beach and in every desert on Earth. Combined, many times over, each star is packed with more protons than any number you can truly imagine. And the weight of all of them, this ocean of stars stretching billions of light years in every direction, traces back almost entirely to the strong force doing its trick, over and over, everywhere, all at once. One force, one rulebook, one trick of turning energy into mass, and from it comes the heaviness of nearly everything that exists. That is the reach of the strong force. It is the source of your weight, and the Earth's weight, and the Sun's weight, and very nearly all the weight in the visible cosmos. Now, honesty demands one careful note here. When scientists study the universe, they find hints of another kind of mass out there, a mysterious substance they call dark matter, which seems to outweigh all the ordinary matter by a lot. Nobody yet knows what dark matter is or where its weight comes from. It remains one of the great unsolved riddles of science. So the strong force explains almost all the weight of the matter we can actually see and touch, the ordinary stuff, while the dark matter puzzle waits in the shadows for a future answer. But set the dark mystery aside and focus on everything familiar, everything made of atoms, everything that glows or burns or floats through space as gas and dust and stars. For all of that, the visible ordinary universe, the answer is now clear and proven. Its weight is mostly trapped energy, created by the strong force, exactly as it happens inside your own body. So you share something profound with every star in the sky. The same force that gives you weight gives them weight too. You and the sun and the most distant galaxy are all built on the same trick, all mostly made of the same captured energy. In the deepest sense, you are made of the same thing as the stars, held together the same way. Which raises a haunting thought. If this one force is responsible for so much, what would happen if it were even slightly different? What if the strong force were just a little bit weaker? Here is a question that keeps some scientists up at night. What would happen if the strong force was slightly weaker? Still there, only gentler. A small change, a tiny turn of the dial. The answer reveals just how much everything depends on this one force behaving exactly as it does. We cannot actually run this experiment, of course. We have only one universe, and we cannot reach in and adjust its settings. So scientists explore this question with careful reasoning and calculation, imagining a universe with slightly different rules and working out what would follow. It is thoughtful speculation, grounded in the math, and what it suggests is chilling. Remember what the strong force does. It grips the quarks inside protons and neutrons, and it also holds the protons and neutrons together inside the cores of atoms. That second job is the one that matters here. Cram several protons into a nucleus, and their electric charges shove them apart hard. Only the strong force keeps them from flying to pieces. It is the glue holding every atomic core together. Now weaken that glue, even a little. If the strong force was slightly gentler, it might lose its grip on the nucleus. The protons, pushing each other away with their electric charges, could win the fight and blow the nucleus apart. And a universe where atomic cores cannot hold together is a universe in deep trouble. Because here is what depends on stable nuclei. Everything. Every atom heavier than the simplest hydrogen needs a nucleus that holds together. Carbon, the backbone of all life. Oxygen, the air you breathe. Iron, calcium, every element in your body and in the world around you. All of them exist only because the strong force is strong enough to bind their cores. Weaken it, and those elements might never form at all. Picture a house of cards built with the perfect touch. Every card leans just right and the whole structure stands. Now imagine the cards were slightly more slippery, gripping each other a bit less. The tower would collapse into a heap. A universe with a weaker strong force is like that collapsing tower. Without the right grip, the building blocks of everything fall apart and no complex structures can rise. In such a universe, there would be no rich chemistry, no planets like Earth, no water, no air, no life, no stars burning steadily for billions of years, no you, reading these words, wondering about any of it. The whole beautiful, complicated cosmos depends on the strong force being tuned just right, strong enough to build and hold the matter that makes everything possible. This is a humbling thought. Your existence, and the existence of everything you have ever known, rests on a single force having close to the exact strength it has. Turn the dial down even a little, and the universe becomes a lifeless scatter of the simplest particles, with nothing complex ever forming. We live in a cosmos that seems finely balanced to allow us to be here at all, and the strong force sits right at the centre of that balance. We have followed this force from inside a single proton all the way out to the fate of the whole universe. But there is a close cousin of the proton we have mostly left in the background, a partner that runs almost the same trick and shares the job of building every atom. It is time we finally met the proton's next-door neighbour. All this time, we have focused on the proton, but it has a constant partner, a particle that sits right beside it in the core of nearly every atom, running almost the exact same trick. That partner is the neutron. And to understand matter fully, you have to meet it. The neutron is the proton's close cousin. Like the proton, It is made of 3 quarks bound together by the strong force. Like the proton, it gets almost all its weight from trapped energy, from the roaring storm of gluons and racing quarks inside it. The neutron plays the same game, storing energy that becomes mass, following the very same colour rulebook. There is one key difference in the recipe. The proton, remember, is built from 2 up quarks and 1 down quark. The neutron flips part of that. It is built from 2 down quarks and 1 up quark. Swap 1 quark for another, and a proton becomes a neutron. That small change in the recipe gives the neutron slightly different properties, including one that shows up right on the scale. The neutron is a touch heavier than the proton, just a little. And that tiny difference comes partly from the down quark being slightly heavier than the up quark, which, as we learned, is a gift from the Higgs field. So here the Higgs plays its small but meaningful role, nudging the neutron to be a hair weightier than its cousin. It is a reminder that even a whisper of mass can shape the character of matter. Now, why does the neutron matter so much? Because atoms need both. The core of almost every atom is a mix of protons and neutrons packed tightly together. The protons give the atom its identity, deciding which element it is. The neutrons act like glue and ballast, helping the strong force hold the whole crowded core together against the electric shoving of the protons. Without neutrons, most atoms could never exist. Picture the nucleus as a tight huddle of players, with protons and neutrons pressed shoulder to shoulder. The protons keep trying to push apart, repelled by their matching charges. The neutrons slip between them, adding the strong force glue that keeps everyone locked in the huddle. It is teamwork at the tiniest scale, and it builds the cores of everything from a helium atom to a bar of gold. So the neutron is a full partner in the story of your mass. Your body is packed with them, sitting right alongside your protons in every atomic core. And they carry their weight the same way, mostly as trapped energy, storms within storms, adding to the number on your scale. When you weigh yourself, you're weighing the frozen energy inside your neutrons just as much as inside your protons. Between them, these 2 cousins build the entire heavy heart of matter. Protons and neutrons, both running the strong force trick, both turning energy into mass, together making up almost all the weight of every atom in existence. They are the twin engines of heaviness in the universe. We have now travelled from the inside of a single proton to the edge of the cosmos and back. We have named the force, proven the math, and met the neutron next door. It might feel like we have finally reached the end, with every question answered. But the truth is stranger and more exciting than that. Even now, even with all we have learned, the proton still guards secrets that no one on Earth has yet been able to solve. You might think that after all this, scientists have the proton completely figured out. We have proven where its mass comes from. We have the rulebook. We have the supercomputers. Surely the proton has given up all its secrets by now. It has not. Even today, this tiny particle guards mysteries that some of the smartest people alive are still fighting to solve. The proton is one of the most studied objects in all of science, and it still refuses to fully explain itself. Let me show you 2 puzzles that remain genuinely open right now. The first is called the spin puzzle. Every proton spins, in a manner of speaking, carrying a property that acts a little like the twirl of a tiny top. For a long time, scientists assumed this spin was simple to explain. Just add up the spins of the 3 quarks inside, and you should get the proton's total spin. Easy. But when they actually measured it, the numbers refused to add up. The 3 quarks, it turned out, account for only about 1/3 of the proton's spin. Only 1/3. The rest, the other 2/3, has to come from somewhere else, from the gluons and the wild motion of everything churning inside. And to this day, scientists are still working out exactly how all the pieces combine to make the whole. The full answer to where the proton's spin comes from is still not settled. It is an open question, being chased in laboratories right now. The second puzzle is about size. You would think measuring how big a proton is would be straightforward, but around the year 2010, scientists measured the proton's size using a new and clever method, and they got an answer noticeably smaller than the older measurements had shown. The 2 results disagreed, and nobody could explain why. It sent a shock through the world of physics. How could such a basic number, the plain size of a proton, come out different depending on how you looked at it? This became known as the proton size puzzle, and it kept physicists busy for years. running new experiments and checking old ones. More recent measurements have helped bring the numbers closer together and calm the storm. But the episode was a humbling reminder that even the most basic facts about the proton can surprise us, and that our finest tools can still disagree about something as simple as how wide this speck really is. So the proton keeps its mysteries. We have cracked the great question of its mass, and that is a triumph worth celebrating. Yet this tiny particle, sitting at the heart of every atom in your body, still holds puzzles about its spin and its size that reach the very edge of what humans currently understand. The little speck is not finished teaching us. That is the strange beauty of science. Every answer opens a new door. We solved the mystery of where your weight comes from, and in doing so we found fresh mysteries waiting inside the same tiny particle. The proton is a bottomless well of wonder, and we are still lowering the bucket. So let us gather everything together now and take one last look at what all of this means for you standing here made of storms. Let us zoom out one final time and see the whole picture at once, from the tiniest speck to you. Start at the bottom. Inside every atom sits a nucleus. Inside that nucleus sit protons and neutrons. Inside each of those sits a roaring storm. 3 quarks racing near the speed of light, a tangle of gluons grabbing each other, a boiling sea of ghost particles flashing in and out, and filling that storm is energy, an enormous amount of it, locked in place by the strongest force in nature. That trapped energy is the secret. By Einstein's rule, energy becomes mass, so the storm inside each proton becomes weight, real weight, 99% of the whole particle. The tiny quarks themselves, the only true bits of solid matter, add up to barely 1%. Almost everything is the storm. Now stack it all up. Trillions upon trillions of these tiny storms fill every atom of your body. Their trapped energy, added together, is the number you see when you step on a scale. Your weight, the heaviness you have carried your whole life, is mostly the energy of countless microscopic tempests, held frozen inside you by the strong force. So here is the truth about what you are. You're not a solid lump of matter the way it feels. You're a pattern of energy, caught and held in the shape of a human being. Your bones, your blood, your beating heart, all of it is mostly trapped force, mostly frozen motion, humming quietly inside every particle that makes you. Think of a flame. A candle flame holds its shape steady and clear, even though the stuff flowing through it is always changing, always moving. The flame is really a pattern, a shape that holds steady while its material streams through. You are something like that flame, a stable pattern of raging energy, holding your shape across the years, while storms churn endlessly inside every proton you're built from. And you share this with everything. The chair you sit on, the ground you walk, the sun that warms your face, the most distant star you will ever see. All of them are the same at heart, mostly trapped energy shaped into objects by the same force that shapes you. You and the stars are woven from the same thread, held together by the same ancient rule. Every atom in your body runs on the very trick that lights the farthest galaxy. This is what the proton has been hiding all along. Behind the solid, heavy, everyday world lies a truth that sounds almost impossible. Matter is mostly energy in disguise. Weight is mostly captured force. The line between the stuff you are made of and the pure energy of the cosmos is no line at all. So the next time you feel the weight of your own body, pressing you into your chair or dragging at your tired legs, remember what that weight truly is. It is living energy, alive with motion, roaring inside you at this very moment in more tiny storms than there are stars in the sky. You're heavy because you are full of captured lightning, tamed and held by the strongest force in all of nature. You are quite literally made of storms, and now, at last, you know where your weight comes from.